Hello, everyone, and welcome to our webinar in which we are visiting University of Rijeka in Croatia to learn about their research on experimental dynamics. My name is Zuzana Fabushova, and together with my colleague Tim Brablik, we are your webinar hosts today. Before we get started, I would like to go over a few items to help you participate in today's event. Here you can see an example of the attendee interface. You should see something similar in the upper right corner on your monitor. You are listening through your computer speaker system by default, but if you like to join over the phone, select telephone in the audio pane, and the information on how to dial in will be displayed. At the end of the webinar, we have reserved time for question and answers. You can send your questions for our presenters at any time during the webinar. Just type them into the questions pane of the control panel. If you experience any technical issues during the webinar, please use the questions pane to send us a message. This webinar is being recorded, and we will share the link with you within a few days after our live broadcast. And now I would like to introduce our guests. A few years ago, the Civil Engineering Department at the University of Rijeka acquired two biaxial shake table freeze, and we were very curious about the research plans they have. Our colleague, Mitch Levy, the application engineer at Quanser, visited the university to help set up the system, and he came back very impressed with the team, with their lab, and the work they are doing. So today we are very happy that the researchers from the University of Rijeka accepted our invitation to talk about their work in more detail. Dr. Gordan Jelenic is a professor of mechanics at the Faculty of Civil Engineering, and he held previous positions at the University of Ljubljana in Slovenia and Imperial College London in UK. His main research interests lie in the area of nonlinear computational mechanics, finite element method, and numerical integration in dynamics. He has published over 30 papers in high-impact journals and ran over half a dozen research projects in Great Britain and Croatia. His fellow presenter today will be Nina Ceh, Ph.D. candidate and teaching assistant in the field of mechanics at the Faculty of Civil Engineering at University of Rijeka. Her main research interests are nonlinear computational mechanics, experimental dynamics of continuous and discrete structures, and contact mechanics. Her focus is on experimental research of dynamic response of small model structures with the use of shaking platforms and optical measuring systems. The other fellow presenter will be Miran Tuhtan, a PhD candidate in the field of mechanics at the Faculty of Civil Engineering, and his main research interests are numerical methods and experiments in the field of non-smooth contact dynamics. And now I will pass the microphone to Croatia.
Thank you, Zuzana, and hello to everybody. My name is Gordan Jelenic, and I will give you a brief introduction to this overview of our research, and then I will pass it on to my colleagues, Miran and Nina, and in the end we will conclude it all together. So we are going to talk to you about research that we are doing on experimental dynamics at our University of Rijeka, with particular emphasis on rocking and self-organization, as well as an example on multiple support excitation analysis. Our core equipment are these two Quanser ST3 shake tables, also accompanied by our optical measurement system, which allows us to precisely monitor the behavior of small structures and small samples in dynamics. And all the research has been supported through the research projects evidence-based characterization of dynamic sensitivity for multi-block structures, computational simulation and experimental validation, which ran between 2013 and 2015, and the current research project configuration-dependent approximation in nonlinear analysis, finite element analysis of structures. These two research projects have been funded by the Unity Through Knowledge Fund and by the Creation Science Foundation. The actual equipment has been acquired through another project, the Research Infrastructure for University of Rijeka campus, financed by the European Fund for Regional Development. My colleagues Nina and Miran and I were actually new to this analysis. So it is very important to say that the design of this lab and the idea for the research originated from our late colleague and friend, Professor Nenad Bičanić, without whom really we wouldn't be talking about this today, because we would never be really made aware of all the possibilities of the research that actually he has instigated here. Professor Bičanić was a graduate of another university in Croatia, that of Zagreb in the capital, and worked as a project engineer in Croatia and the Netherlands, and later he joined university world and became academic and associated with University of Zagreb, Boulder, Swansea, Rijeka, and Glasgow. In Glasgow, he was also head of the department and Department of Civil Engineering, and he was one of the founders of the National Society for Applied Mechanics in the United Kingdom in 1993. Among many other areas of his interests, let me mention dynamics and seismic analysis, which is in fact very relevant for this today's presentation. During his lifetime, he has made 30 people PhDs. And we miss him very sorely. He sadly passed away 2 years ago. He would be very, very happy to be here with us today, otherwise. The idea for this research came about by really thinking about how we are bound to analyze discontinuous structures. And to do so, we often have to perform some sort of homogenization just to be able to apply eigenanalysis, which is typical of continuous structures. And we often have to repeat the analysis for many different variations of the internal parameters. So the idea was really to set up a set of rather simple, small benchmark problems in which we would be able to analytically and numerically and also experimentally run and have reliable answers to simple questions, to simple mechanical problems, so that we can actually validate our commercial programs against these examples. What we have in reality is sort of monuments like this fortification in the upper figure, where if you look at the spike at the very end, you would realize there is absolutely no mortar, there is absolutely no connection between the stones there, and obviously it has withstood the test of time across some centuries, I'd say. And in the bottom figure, you see an example of vernacular building, which is very typical of our Mediterranean area, and it's also spread across Europe, where again you have just a completely drywall structure, which, as I said earlier, is unable to really be analyzed using methods of continuum mechanics. The actual motivation for the analysis came from something that was very relevant and still is relevant in Europe, and this is the need to reset our nuclear power plants for the next 30 or 40 years, or whatever the duration of the nuclear course. When they were built this amount of time ago, the idea was to close them, but nowadays the energy requirements are different, and many countries in Europe often think about how to just renew their life. What happens there is that you have such honeycomb structure in which you have these nuclear cores which burn. And nobody really knows what is happening with the actual structure, which has to be discontinuous because of the high temperature gradients that these blocks are exposed to. So in fact, how they react to seismic excitation is something that is really more guessed than actually known. The idea for this research came about also by or actually the way how to operationalize this idea was to concentrate on some simple blocky structures or stacks of these structures, and to analyze how they react to seismic ground excitation or some other sort of ground excitation, and see whether they continue to rock in a stable fashion or overturn or just simply translate with the ground. Our basic two research questions are: can we characterize the behavior of an ordered blocky system? And by characterize, we mean, can we predict the range of dynamic sensitivity to external influences, such as, for instance, the ground excitation? And also, can we come up with a number of suitable sensitivity indicators which we can measure and compute, and which are really informative, which can illustrate to us very clearly the performance of the system. This is how our structural dynamics lab looks today. So again, the main part is these two shake tables, and we have the optical measurement system, as I said, with appropriate software. We also have some other equipment which we occasionally use, but we won't be talking about that today. And we have made up a little corner, as I showed you here. Now, when you enter our structures lab, it looks like this. So this is the whole structures lab, and on the right side you see our little seismic corner. What I forgot to say is that on top of this, we also have one small ST1 platform. And what happens next is my colleague Miran will tell you something about the research that we have conducted on this.
Thanks, Gordan. My name is Miran Tuhtan, and in next part I will talk about my using of STI-40 platform. And the subtitle of my part is Assessment of Rocking Stability of Rigid Rectangular Block Standing on a Deformable Elastic Beam due to Continuous Harmonic Excitation. And in the next couple of minutes, I'll try to explain these bolded phrases in this subtitle. And here you can see the system we use. This is the shaking table STI-40, and above it, you'll see what's there. So first thing to explain is deformable elastic beam. Here you can see three of them. They are made from balsa wood, which is very soft and elastic. So we've made different thicknesses, so we can try to explore how different thicknesses and different elasticity helps with the rocking stability. Here is the video example of its elasticity. So here you see my finger pressing not that hard, and deformation is highly visible. Next thing to explain is rigid rectangular block. This is presented here. This is aluminum block of size 3 by 3 by 13.5 centimeters and about 300 grams, or for you using imperial system, this is a bit more than 1 by 1 by 5 inches and 3/4 of a pound. And on the right, you see that even this 300 grams, when you put on this base, is already deformed. Next thing in the subtitle is continuous harmonic excitation, and here you see sinusoidal wave. This is something that most of us think when somebody says harmonic excitation, and this is first type of excitation we did with our platform. And this was all well until we realized we have a problem here at the beginning, and the reason for that is here you can see the amplitudes as they are changing in time, and this is sinusoidal wave, and velocities of this motion are cosine waves, meaning that here where you have the maximum amplitudes, you have zero velocities, and vice versa, where you have zero amplitudes, you have maximum velocities, which is okay here, but here at the beginning, when you start the experiment, you don't have maximum velocity, but you have zero velocity. So we need to modify our VI, how do we do experiments, and we came up with this kind of graph. This is roughly divided in three parts. First part is the ramp up period, so we slowly increase our amplitude from central point to the maximum amplitude. Then in the second phase we have a pause, so we allow our block and the system to stop shaking and movement, and then third part is cosine wave, well, similar to this top graph which we use to see how block moves. And the last thing I'll explain is the first part of the title, that's assessment of rocking stability. And we have three types of motion of block. First is translation, and here you can see the parameters used, so 0.5 centimeter amplitude and 1.5 hertz frequency. And here in the video you'll see all parts of motion. So first is calibration of platform, then it's ramp up period, a pause, and now after a pause whole system starts to move, and as you can see block moves together with the base, so there is no rocking. Block is having translation motion. Second type of motion is overturning. So for bigger parameters of amplitude and frequency, you have higher accelerations. So what happens is shown in this video. So once again, this was calibration, ramp up, pause, and now it will start to move. And as you can see, the block fails quite fast. And the third, and for us the most interesting part, is the stable rocking, shown in this video. And once again, same thing happens. First is calibration, then it's ramp up period, it's quite small, then it's pause, and after that the block starts to shake, and you see it's stable rocking, it doesn't overturn. And also I hope you can see that this base also moves and vibrates because of the impact of block on the base on every turn. So basically what are we doing? We are testing different base thicknesses for different parameters of amplitude seen here on y-axis and frequency seen here on x-axis. And here you can see our numerical results, where this yellow part represents the stable region. And we wanted to try to evaluate this experimentally. But you need to have in mind these limitations of STI 40, which are the travel is maximum 2 centimeters, maximum frequency is 5 hertz, and not only that, the maximum acceleration is 1g. That means from whole this picture, what we can test is basically only this bottom left part. So as you can see, it goes to 2 centimeters, 5 hertz, but not both. So here, this region, which is here in this numerical part, and it's quite interesting because it becomes stable region, we could not test at on STI 40. So for future, our plan is to repeat these experiments on our bigger platforms, and more about them and some quirks and limitations of them will tell you Nina in the next part.
Thank you, Miran. My name is Nina Ceh, and I will present you the part of our research that is done using biaxial shaking table ST3. So here you can see that we have this shaking table ST3. For example, you can see it running when subjected to harmonic excitation in both directions. And along with that, we have an optical measuring system with 2 cameras, which enables us to take the video of the whole experiment, and after post-processing the video, to get the information about 6 degrees of freedom in 3 dimensions of everything that was in the video. What we are doing is we are trying to dynamically characterize the rocking of blocky structures, and again, similar as what Miran explained, we are involved in rocking of one single block that is, in this case, on a rigid base. And this block can only rock, so it cannot jump or it cannot slide relative to the base. From simulations of this rocking motion, we can see that when this block is subjected to some kind of ground excitation, it will start rocking, then it will change the center of rotation, impact the base, and at the end settle. But for example, if we slightly change this ground acceleration, the block will start rocking and then will overturn. And we are specifically interested in the conditions that make the rock overturn. So this research actually considers the acceleration function, which is a single sine wave like shown on the top graph here. And it is given as an input to our numerical simulation. So we give the acceleration time history, and all the results are shown with respect to amplitude and frequency of this acceleration. I will show that a bit later. So the results from our simulation are whether the block is overturning, this is this inner part of the blue line, or the block is rocking, shown with respect to amplitude and frequency of the acceleration function. The amplitude and frequency are here both scaled with alpha times g or with p. Alpha and p are parameters that are depending on the geometry of the block. And researchers until now used this graph considering the alpha, which is a parameter describing slenderness of the block, but for every size of the block. And this inner part represents the overturning conditions where overturning happens without the impact. So the block starts rocking and it immediately overturns. While this smaller part represents the overturning, which happens after block rocks a bit, so it impacts the base, and after that it overturns. Well, in the past few years, researchers came to a conclusion that during rocking motion, when the block transits from rocking around one corner to rocking around the other corner, and specifically at the moment when it impacts the base, the position where the impact impulse acts does not necessarily have to be at the very edge. It can be at any other point along the base of the block. And also, for larger blocks, this position moves from the edge towards the midpoint of the block. As this position moves, this means that the block loses less and less energy. So it means that if we have larger blocks, this area of overturning that happens after the impact becomes much, much larger. For example, as the one you can see on the right picture. And specifically, we want to validate these conclusions experimentally. The blocks that we are involved here have the height to width ratio 4.5, but we have blocks of 2 different sizes. And this red is the boundary between overturning and rocking area for the smaller block of this slenderness, while the green is the boundary between overturning and rocking area for the block with, again, the same slenderness, but a larger block. What we are now experimentally validating is this part of the graph. The left part of the graph is not really interesting to us because there is no size effect visible here. And the upper part of the graph, it is really interesting, but in this case, for this geometry, we are not able to reach these kind of accelerations, considering the limitations of our system, of course. So if we want to get this kind of acceleration that we use also as the input into our simulation, in our shaking table system, we have to actually input the the displacement function as this one shown below, which is a linear function plus a one sine wave function. This kind of function satisfies the conditions that the initial velocity of the system is equal to 0, which means that we don't have some kind of jump in the acceleration function at the beginning. Our shaking table system is actually run by softwares which are written in LabVIEW programming language. And since we have the code behind the softwares, we were able to modify all the softwares in able to get this kind of displacement profile as I shown earlier. Our experiments looks like this. So we have two blocks of the same height to width ratio, but two different sizes. It may seem that these are two blocks, but actually this is one block and this is one block. And after subjecting these blocks to some kind of ground excitation, so we can have different behavior. For example, these are the blocks subjected to one ground excitation, where you can see that both blocks start rocking and after some time they settle. This rocking motion will be represented with blue crosses a bit later on a graph I will show with results. On the other hand, if we have a bit different ground excitation, like this one here, you can see that the both blocks start rocking. Top block settles after a while the smaller block actually overturns, which means that the larger block can actually sustain an acceleration that is able to overturn the smaller block. So here are the results from a test of experiments we made. On the left picture, you can see the results for smaller block. The purple line is the boundary from the simulations, while the red axis and the blue crosses are the results from our experiments. So the boundary between overturning and rocking is roughly validated experimentally. On the right side, you can see the same result, but for the larger block. Again, the boundary between overturning and rocking is roughly validated experimentally. Now, the bottom part of the graph, it's not really interesting to us, but we could go into this part. Here we have low frequency and low amplitude of acceleration. And this yellow curve represents the real behavior that is done by the shaking table, which is really close to the blue line, which is the input, what we want the table to do. But the upper part of the graph, which is pretty interesting to us, is the part where we already reached table's limitations. So here we have high frequency and high amplitude of the acceleration function. And we can see that what the table does resembles maybe a bit more to a double constant pulse excitation than it does to this sinusoidal curve. So we have to be really careful here. The research that we are doing now is assessment of rocking stability of a double block stack. So we have a stack that consists of two blocks, one on top of the other. And during rocking motion, this stack can go through these 8 different patterns of motion. And it continues to transition from one pattern to another back and forth. For example, you can see here that the stack of blocks was started to rock in a way that only the top block was tilted. But after the impact between the top and the bottom block, both blocks started rocking together. So it transited from one pattern of motion to another. And this kind of behavior we want to also be able to notice when this stack of blocks is subjected to some kind of ground excitation. For example, here you can see an experiment where the stack is subjected to harmonic ground excitation of shorter duration. And even though you might not be able to see that on the video, at some points when the impact between the stack and the base happens, there is some kind of gap occurring between the top and the bottom block. So actually there is transition between different patterns of motion. And another research that we are doing with biaxial shaking table is we are trying to investigate the conditions for pattern formation. So we have some kind of a basin with small spheres at the bottom of the basin, and on top of that spheres we have an assembly of rectangular discs. And what we want to see is if we subject this kind of basin to some kind of harmonic excitation of a certain acceleration and frequency, whether we will be able to see some kind of periodicity in its behavior, maybe rarefication and compaction patterns, and whether we will be able to notice undesirable events. Just to show a little bit better, these are the two examples of two experiments where an assembly of 4 large disks or 8 smaller disks is subjected to sine sweep excitation of the shaking tables. These videos are slowed down, so this is not the real velocity. Now the examples I'm going to show are not with sine sweep excitations. Here we have harmonic excitation that is long-lasting. And in the first example, we have 4 blocks inside of the basin. And the excitation has the amplitude of 40 millimeters and frequency of 1 hertz. The blocks are with different colors, so it is easier to track their positions in this graph. So here we have the positions of the boundaries of the basin and of each of the 4 blocks during time. And first we tried to track the centroid of this 4-block assembly during time. And from this, we cannot see any kind of periodicity. The other thing we try to track is the inertia index of this assembly, which means that we calculated the mass moment of inertia of the whole assembly with respect to its centroid and divided it with the reference inertia. And again, we cannot see any kind of periodicity in the behavior. But in another example, where we have 8 blocks inside of the basin, and they are subjected to harmonic excitation with amplitude 75 millimeters and frequency of 0.5 hertz. Again, we can see the positions of the boundaries and of the blocks during the experiment. And if we try to track the centroid in this case, we can see that there is high periodicity in the movement of the centroid after some transient response at the beginning. And also, if we again try to trace the index of inertia, we can also see that there is some kind of periodicity in this index, which means that we actually have periodic rarefication and compaction of the whole assembly. That means that multiple impacts happen between the bodies during the experiment, which indicates that this kind of assembly could damage much sooner than in some other case. Now I will leave you back with Gordan, who will show you the last part of our research.
Thank you, Nina. And finally, what we did the last spring and summer, we had a final year student with whom we did some research on multiple support excitation. Here you briefly can see our model. It's a simply supported beam lying on both tables, and it's supported by both of these tables, which supports are then given some initial impulse. The motivation for this research came from the observation that in large span bridges in earthquake-prone areas, there may be some time lag between the impulse reaching the first pier in a suspension bridge and its second pier, which may be 1 kilometer or 2 kilometers apart. We don't have such bridges here, but just to give you a picture, this is a bridge on the outskirts of Rijeka, our city here, which was built 38 years ago, and at the time it was the largest pre-stressed concrete span arch bridge in the world. It's not anymore, but this is an example of a bridge that has moderately or largely large span for its type of 390 meters. Okay, back to our example. So this is again the picture of our example. As you could see, we have added some concentrated masses on our beam so as to emphasize its modes of excitation. So to go back to the scheme that Nina already showed you, we now have both shaking tables which we are capturing with our optical measurement system, and they are both given some ground excitation in a specific fashion that I will describe. The actual model has these properties, so it has certain length, certain mass, concentrated masses are also given. Wood is a soft wood of the Young's modulus as given here. Second moment of area is easily computed from the cross section, and it is from another experiment that the Young's modulus is obtained, and from yet another experiment that the damping ratio is obtained by just observing the history of evolution of the logarithmic decrement. For this example, the first resonant frequency and the second resonant frequency are given here in the right-hand column, and just underneath we have the approximate values of the frequencies that we have given to our shaking tables so as to simulate resonance. The experiments have been run with a very, very small excitation amplitude given to the tables of just 1 millimeter. Okay, and you will see in the videos how this excitation amplitude is actually magnified due to the fact that we are nearing resonance frequency. Okay, theoretically, we are talking about the equation of motion, right? Mass times acceleration, damping times velocity, stiffness times position equals to some external force. When we apply the modal analysis, this system of equations of motion actually splits down into a number of independent equations of motion, which are easily solved. And this is the solution, of which the last part is of particular interest. This is the steady state part. The first one is the transient part that dies out very quickly. And the steady state part is the one that we will be focusing on, in particular, its amplitude, where we can see that the actual given amplitude is magnified in the proportion, well, magnified due to the fact it's magnified when the excitation frequency comes close to a natural frequency of the system. In that case, you can see in the denominator that it gets very close to zero. The only reason why it's not actually zero is presence of damping in this term here. Right, and there is also some time lag, but let us focus on our amplitude. And again, back to our experiment. So our wooden beam is enriched with our concentrated masses given at the quarters of the span, and then we have some simple supports which are printed on a 3D printer and which are attached to our shake tables, which are given then ground excitation. And these are the cameras that monitor the motion. Right, so what we have is basically two important and interesting situations. We have first resonant frequency and second resonant frequency. When we give the excitation near the first resonant frequency, what we expect is that the symmetric modes of excitation will pop up. And later, when we repeat the experiment with asynchronous excitation, where the displacements of different magnitude by same frequency are given to the supports, then we will of course expect the skew symmetric part of the motion to surface. But let's go back to this example here. Now we prescribe displacements to our platforms in unison, completely synchronously, as you can see it here. So they ran in both directions at the same time. Now, of course, the actual magnitude that we are given now in our experiment is much, much smaller. It's only 1 millimeter, so you won't be able to see any motion in the tables. But look at the beam. So it's the first excitation frequency, and of course, the symmetric mode of the symmetric shape of deflection is something that can clearly be seen. This is also visible in our graphs, which in fact shows that this symmetric mode of motion is in fact our first mode of motion, which is in complete correspondence with the fact that we have given first resonant frequency, not the third one. Now, when we give asynchronous excitation with the frequency corresponding to the second resonant frequency, again with the same amplitude, so that the tables move like this. Oh, sorry. Tables move like this in the opposite direction with respect to one another. Again, we give it with a smaller amplitude of just 1 millimeter. And what we obtain is such a motion of our beam, which again reflects the fact that we are very close to the second resonant frequency, and only the skew symmetric part of the motion is clearly visible here. We have had many other plans to do with our research, but we didn't manage to do all of them. Let me just mention, just to close it up, that such kind of research is important when it comes to actual real seismic signal, like the here presented Northridge 1994 ground excitation, here plotted in red, and in green you could see the motion of our center mass. So it somehow, on average, follows the motion of the supports, but it has some additional peak at the beginning and relatively small departure from the position of the supports later on, which again die out with time. But now, if we repeat it by just giving the time lag of 1 second between the supports, then we can see quite a different answer. There is no such a large impulse at the beginning of the motion, but the actual response of the structure later on is much more pronounced in its displacement than it was earlier when we gave the synchronous excitation to both supports. And with this example, I would like to close this presentation. Thank you all for your patience, and give the word back to our Quanser partners.
Thank you for a very interesting presentation. I think there was a lot of interesting stuff and a lot of interesting research. And we have a couple of questions from the participants. The first one is a question regarding the experiment with two-block motion. In this test, it seems like that you tried the test in lower frequencies. Have you also considered higher frequencies in your experiments?
Yes, actually with the two blocks, we want to conduct roughly the same series of tests as we did with one block. So we want to know what the behavior will be with respect to different amplitudes and different frequencies of the acceleration. It's a research that is just beginning, so I showed just one example that we did. But yes, we want to cover the full area of different excitation amplitudes and frequencies. And actually, what we are particularly interested in is whether, for some kind of conditions of the excitation, maybe in some case only the top block will overturn, or in some case the whole stack will overturn altogether. So we actually want to get the conditions that make only partial or total overturning of the stack.
Thank you. Regarding the first and second part of your presentation for stable rocking motion, have you calculated coefficient of restitution? And if so, the difference you have found between the experimental and the analytical is considerable?
Yes, we have calculated the coefficient of restitution from a different set of experiments. So first we conducted experiments with free rocking motion, where we have the blocks tilted at the beginning, and we just leave them from this initially tilted but zero velocity position. And using our set of cameras, we track what happens in the experiment. And from that we can get the coefficient of restitution, so actually the energy loss during each impact. And this coefficient of restitution is used to obtain the graphs that show overturning or not overturning conditions that I showed earlier. And what we want to do now is we want to experimentally confirm that these graphs actually show the overturning of the block during some kind of a seismic or some kind of ground excitation. And yeah, another thing to comment about how different are these results from the results from the literature or from the equations that are available where, well, if somebody is working with rocking motion, the first equation for the restitution was given by Hausner, and it was used many years. And what we were able to see from our experiments is that the actual restitution is not so close to Hausner's, because Hausner assumes that the contact occurs at the very edge of the block and that the contact impulse acts at this point. But what we were able to see from the experiments is that the impulse actually acts at a point that is further from the edge and closer to the midpoint of the block, which means that actually the restitution is actually different from Hausner's. There are some formulas that describe this restitution much better that were introduced in the past few years, and experimental results are much closer to these improved formulas that were recently introduced.
And as for the first part, this is really an ongoing research, just the same, but even more so. So we have started investigating the situation of rocking on a flexible structure, just because we were intrigued to see whether flexibility adds to the stability or actually is detrimental to the stability. And we have made a small computational model with which we are not very satisfied. We have to improve it. So this is a reason why we have not shown it yet. And also we have not played with any restitution there, apart from the original Hausner's mentioned by Nina earlier. So basically we have wanted to have as large as possible a pool of experimental results on which we can then build and hopefully eventually come up with a good numerical model.
Thank you. The next question is your lab open to collaboration with other universities?
Absolutely.
Of course. This was an easy question.
Do you have any examples? Are you working on anything with institutions from outside Croatia?
Yes, we have just started an international project with a colleague from Dalian University in China, who I think also possesses one of your platforms. So we are running a joint Croatian-Chinese 2-year bilateral project, and we hope to learn from our colleagues in China, and hopefully they will also be interested in our dual platform system. That's the first thing that comes to my mind, and the collaboration that has come closest to the actual fruition, and also through the earlier Universities or Knowledge Fund, we have established contacts with the University of Oxford and also University of Durham. So with the Department of Engineering in the University of Oxford, we have actually conducted some experiments during the lifetime of that project, and we are continuing to doing so. And we also have some contacts with some industry in Britain, with Atkins Nuclear, and also with British Energy, who are interested in some of our benchmark tests to validate the software that you use for their well, everyday work.
I have one more question. Are you using the lab and the equipment also for teaching activities?
For teaching activities.
Oh yeah, definitely. That's how we made interested our graduate students to join us and to do the multiple support excitation final year project. It is actively used on the course called Dynamics of Structures. It's a 4th year course for our undergraduate students. And it's actively supported by the lab exercises, through which the students get well, acquire, they get to know our equipment, and they get to like it, and to get more interested into doing their final year projects when they know that it's something to do with the lab experiments also, not just the theory. So yes, we definitely are using our equipment for teaching purposes. This is just one example, and we also have different equipment which we use in different courses, just the same.
Another question just came. How did you scale the ground motion in a shaking table? What kind of scaling method did you use? Only changing amplitudes?
I don't know whether you're thinking about the earthquake motion that was shown at the end, or well, the earthquake motion was just scaled using the maximum displacements that the table can simulate,
basically in the VI that represents the Northridge earthquake, this scaling has already been done so as to maximize the performance of the equipment. We have not really scaled it any. We have not done anything other than that, and for the present really do not have any particular experiments with scaling. As you could see, we have done our experiments on a simple model that is not a model of the real structure, so that such a scaling would really be necessary to obtain an answer as to how the real structure will actually react when exposed to such an earthquake.
Another question, are you able to introduce a real ground motion into the system?
Real, you mean in terms of amplitude and frequency? We are limited again by the technical performance, technical specifications of the equipment, which specify the maximum amplitude and maximum frequency that are given. And as for the shape of the motion, if that was the question, yes, we are able to create VIs that can simulate it, at least in principle. We have not modified too many of them, but we are learning how to do so.
Okay, and I think this was the last question that we have. So I would like to thank all our participants today. Thank you to Dr. Jelenic, Nina, and Miran for a great presentation and sharing your insights with us. If there are more questions for you, I will definitely share your contact information with the participants, and if they have any other questions, they can direct them to you. We have recorded the webinar, so within a few days you will receive an email with the link where to access it in case you want to revisit it or share it with your colleagues. If you want to learn a bit more about the platforms that Quanser can offer to do a similar research or for teaching, you can visit our website. And I would also like to extend the invitation for our next webinar, which is scheduled for April 26th. We will again discuss research, but this time it will be research at the undergraduate level. Dr. Mike Fry accepted our invitation to talk about the work in the field of unmanned vehicles at University of Incarnate Word, and how, despite being a small university, they were able to get funding and build one of the largest undergraduate labs focused on unmanned systems in the United States. This might be not exactly the topic for our today's audience, but if you have colleagues that might be interested, feel free to share it with them. And thanks again, Dr. Jelenic, Nina, Miran, for your time for the presentation, and I'm looking forward to seeing you online some other day.
Thank you, Susanna. Thank you for inviting us, and thank you for giving us the opportunity to participate in this experience. That was a great experience for us.
Thank you.
Thank you.